Close these windows.
Sometimes the one in the surface will become one coming in, one going out, but you have to have multiple layers.
Yeah. Then all the
Right.
Is mic work?
Turn on.
Oh.
Okay, thank you. The next talk we have is from Girsh Blumberg from the University of Rutgers, and Raman scattering from chiral materials.
Now it's working.
All right. Well, first of all, thanks for inviting me. That was kind of a surprise invitation. And I agree with Peter's comment. I mean, I did expect a little bit warmer weather here at that point when I was planning to come. Okay. Now, I was planning to talk about some relevant but related but different subject, and I got inspired by Leon's talk yesterday. We spoke very briefly after Leon's talk, and I decided that I will give you some overview and explain how I think Raman can grow chiral modes and say much more than any other probe can do. This is entirely ongoing research carried out by, well, really the first, well, starting graduate student. It's not advanced talk. I'm giving it, I put it on my labs last night, and I never gave this talk, so it's not polished presentation. Nothing is published. Okay, so, but I would appreciate if you ask questions immediately so we don't need to wait to that. All right, so I don't need to explain what chirality is. That, well, an object that doesn't have a mirror symmetry, so I need left gloves for my left hand and right gloves for my right, because there is no mirror here. So if the mirrors are broken, then the system is chiral. This is not common in Raman literature. Textbooks don't talk about that, and tables don't show that, but some smart people, so this paper is now 65 years old, who very carefully derived Raman tensor for all-point groups. Already, he didn't say that explicitly in this paper. This is the Russian-style paper, which is 2 pages long and contains everything about Raman spectrum. But it does contain that statement that if the system is chiral and we come in with, so I'm talking about polarization resolved Raman scattering. So I'm coming in particular polarized light and detecting it. And I will talk today only about circular polarized light. And I'm coming with right polarization, photons with right polarized photons, and detecting the photons which are left polarized, versus I'm coming with left polarized photon detecting. Okay? And in most cases, you would expect that this will be the same. In fact, I have been doing Raman scattering for maybe 40 years. And I never saw an obvious observable that left right is different from right left. So I assume that this is always the case. People knew that it's not the case. I mean, literature research shows that, well, this is now 50 years old, and people were talking about effects, which are 10 minus 3.1% is the difference between right and left. So this is molecular spectroscopy for some. It doesn't matter really, Raman, so we say. Now, the surprise for me was a very recent paper where they claim that by doing essentially this experiment, they call it circular independence Raman scattering, they detect substantial difference between left-right and right-left polarization. And that caught my attention, and I tried to focus on that and understand that. So me and new graduate student is trying to do that. And what they were studying is this system, 1T tantalum selenide, tantalum sulfur, disulfur. So this system, I Googled that at that point. I got 15,000 publications, not quite high TC, that's 10 in the fifth. But if we have 10 in the fifth publications, we know for sure that we don't know the reason for high TC to 10 in the fifth. So here we also don't know the reason for charge density rate. So it's quite complicated system. At very high temperatures, about 450. It's a simple unit cell. It's a layered structure, van der Waals, very simple. Then on cooling, there is a cascade of first order charge density wave transitions, and people keep arguing what the origin of that is and what the phases are. They are called incommensurate density wave, then they call near commensurate density wave, then they call commensurate density wave, and the resistivity is changing from metallic to really good insulator by many orders of magnitude on cooling of that system. So the main motif of that density wave is that it involves 13 titanium sites, so that titaniums are between the sulfur layers. And there is this movement of 12 titanium sites towards the central titanium, forming this so-called Star of David motif. That people knew already for a very long time. Now, what was done in this experiment, this paper, a couple of years ago, was the following. They had a flake, and they measured the Raman, and well, the red one is right-left, and the blue one is left-right. And well, surprisingly, they saw a different spectrum. And then they flipped the flake and measured the flake from the same flake from other side. And they found that, well, their colors are changing, right? So the left-right became right-left. Now, what caught my eye is that, well, the modes that they see are actually different modes. It's not that you have one mode and they have different frequencies. And there is a region, of course, where there is the spectrum is same, and then the region where it's different. And what I neglected to say immediately, that if I would use that knowledge which was provided to me 65 years ago and do the proper calculation of Raman tensor, I will develop that a little bit later. But what I expect is that if I have two domains which are equivalent domains, but one is right-handed, another is left-handed, and I'm doing these excitations, I would expect to see the same modes, except that for left-handed domains, I will see them only in right-left polarization, and for right-handed domain, only right-left polarization, not in both. So that's how. But I see here different modes. They didn't explain that in paper. The only other thing they did is that they did the integrated intensity here, and they're plotting normalized difference of this red versus blue integrated. And well, they see something that looks like another parameter. And here the system is chiral, and here the claim the system is chiral. So I thought that maybe it's good time to get a little bit deeper here. So at high temperatures, well, above the charge density wave, the point group of the system is D3D. It has mirror. So that's why it cannot be chiral. And for this group, when we do right-left and left-right polarization, I don't want to derive Raman tensor, etc. here. It's technical, we can discuss that. But I'm coupling to this EG representation, which is two-dimensional representation of that group. And it doesn't really matter whether I'm measuring right-left and left-right, and that's what happens with most materials. Now, then the distortion is, well, the distortion itself is not a problem, but then they argue, and that was known from STM for a long time, that the star of David, they get some particular alignment, and this alignment has an angle, so that there is a rectangular lattice of the star of David, and the stars have an angle relative to the crystallographic axis of the pristine crystal, and that rotation is something 14 degrees. And that rotation can happen either with plus sign or minus sign, and that gives the chirality. So it's really the geometrical orientation of stuff. So that was known from STM for a long time. In that paper, they do also, in this paper, they also do ARPES, they do STM, and well, in ARPES, they see for the band structure these windmills. So you have left-handed windmill, right-handed windmill. So directly seeing the system is chiral. And that's what they believe it is. Now, so we decided to try to do it more carefully. We are doing temperature dependency. Everything I'm going to talk is this in this right-left. It's cross-circular polarization. I'm not doing anything else. At very high temperature, there's only one Raman allowed mode in EG symmetry, and it's this mode around 250 millinumbers. And then on cooling inside the incommensurate charge density wave, the new modes appear. There's some interesting electronic scattering also that appears. And then when we get to this non-commensurate charge density wave, which becomes chiral, the moment. So all these modes are signifying the modulation, density wave modulation, increase of unit cell folded modes. There are also amplitude and phase modes and all kinds of things. So it's all complicated. All right, but what is important here to notice is that while in high temperature phase we have this point group D3D, now when we organize in some kind of density wave pattern, we break the mirrors. We don't have the mirror symmetry anymore because of this odd angle. And when the symmetry is broken, mirrors are gone. So these mirrors are gone. We reduce the group to C3I. And in that group, this is again now, one has to be very careful with literature and everything that you can find in tables online, etc., because they still call this EG representation. Actually, this isn't the generic representation, but it's two one-dimensional representations. So if you don't have the mirrors, this EG representation are essentially accidentally the generating applied field they will split. And they're built out of, well, in this case, one line transforms like x squared minus y, well, it's called d plus id, and another one d minus id quadruplets. That's what they are. And now that explains why you make these excitations out of chiral state, and one light can couple only to one line of this representation. The other line can couple only to another line, but they are still degenerating zero field if time reversal is not broken. So you should see the same modes, except that if you would have a domain of a single chirality and you do the measurement from here and then you do the measurement from here, in one case you can only see signal in right left, in other case you can only see signal from left. And this is not what happens in this data. So we did our own data, which looks nice in that sense that the modes are sharp, and this is room temperature. That's what they did initially. There is some number of modes. One of them is fundamental mode that exists very high frequency. Everything else is due to density waves. There is some region of electronic scattering where the chirality doesn't matter. But in this region where the phonons are, you can clearly see and heavy modes, the low frequencies are coming from heavy atom titanium modes, and this is sulfur modes, this combination. But you can see that the frequencies are different and intensities are also different. And that means that this density wave arrangement is much more complex than this naive representation that they had here. So I'm plotting here for the question. I'm plotting here Raman optical activity, which is one spectra minus other spectra normalized to the green line where those spectra coincide, I get zero. And then, well, technically I expect somewhere be 1 and some be minus 1, but I have stuff in between here.
Is this a high temperature or?
This is room temperature so far. So it's room temperature, it's inside that nearly commensurate charge density phase. And this is the temperature dependence of this, temperature dependence of this function. So this noun phase transition is here at 350. So this is the transition from non-commensurate to nearly commensurate phase, where according to this paper, the chirality sets in. We clearly see that, except again, the scale doesn't go to 1. The blue lines are at different frequencies than the red lines. And more importantly, what we instantly saw that there is actually 2 transitions. There's some onset already here, and some modes already developed there, and then additional chirality develops at the second transition. So we have 2 coupled transitions that already tells that the picture is more complex. Now, I'm doing with time,
You have about 10, 15 more minutes.
10, okay, very good. So, so I was very puzzled. So the puzzles were the following. So first, I see two transitions, and that hasn't been noticed in this. Well, I didn't check every 15,000 papers, but it's not common knowledge. Second, that I did expect actually see the same spectra if I'm measuring from this side of lake and the other side of lake, but by flipping the polarizations. Instead, I see on each side, I see both right-handed and left-handed plates having contribution at different frequencies. And if I have a crystal, I cleave it. This data is taken from cleaves crystals, but there are two parts of it. And I measure the other one, then the blue color and red colors will switch. So that part is fine, but I have multiple contributions to that.
Girsh, I do have a question.
Yes,
So,
sir.
if I have a screw, like a normal screw,
Yeah.
and I flip it around, and it looks exactly the same. So I don't see what this point about flipping the crystal around.
You're looking on that screw from different side now.
Yeah.
From above or from below.
Yeah, it looks the same, right? It's right helix screw, and it's
It's helix, but relative to your photons that are coming, in one case, the helix is this way, another case is helix in the
I take it, I take the sample and I flip it around. You're saying I get a different chirality?
You cleave the sample, you have two parts. And if you measure this part, you get this spectra as shown here. If you, or let's take linear example here. And if you measure the other one, I would need to switch. If I switch this, I'll get the same thing. Experimental fact.
Yeah,
You
but that's
can
not
make
what,
a-
but that's not what a screw does, right? Like that. The screw looks the same when you flip it around.
Screw looks the same. Now, what is your coordinate system? Are you in coordinate of lab or coordinate of photon? You need to. So your photon is circularly polarized coming in. If it comes in, it's along the screw this way. Now, if it comes from below, it's against the screw or along the screw.
I thought you said you took the crystal, flipped it around to look at the backside. It has a different helicity.
I didn't say it has different helicity. I said I need to split this right and left joke. Okay, so that's what it is. Okay, now, so I was very, very puzzled with the situation, so that I mentioned these two main concerns in interpretation that people published. And I stumbled on this paper. It's an STM paper, relatively recent, and there was another one from 23, done in Clark University. And in relation to machine learning, this is really talk of human intelligence. It's instead of artificial, they did it everything manually, but it's an incredible work that has been done based on the data. So they do STM, they get the STM like everybody else can. I mean, these days, this data, they do Fourier transform. They discovered that the satellite peaks are actually not a single peaks. They have better resolution. They notice that there are multiple peaks here. And then they do reverse engineering, very careful reverse engineering to find out what really happens. And according to them, there are these clusters of star of David, these distortions. And this is now in the chiral phase in the near commencing density wave phase. but the star data are not formed by just directly moving the tantalum atom towards center. They are moved with some rotation. So these arrows here that showed, I don't know whether you can see them from distance. The arrows here are, so the beginning is in the center where the atom would be in high temperature phase before density wave, and it shows how the atom moves based on the model that they carefully. So, and they derived that there is a lattice of these domains of star David. Those are, each of them is roughly a star David, but it has chirality built in that domain itself. And then there is a stuff in between them, in between domains, which has chirality which is opposite to the chirality of the star David. They do temperature dependency. They measure only 3 temperatures. Well, they say at the second paper that they are working on that. So this is everything here is below the nearly commensurate phase transition, but they find that the angle behaves like an order parameter, and there are 2 of them. So this angle is related to what happens inside that domain. So, and there is another angle which is this. Remember, initially we had the 13 degrees arrangement of these domains. So this arrangement turns out it's temperature dependence. Low temperature is 13 degrees, but then it gets decreased, and at 350, we leave phase transition, it goes away. Well, that's the knowledge that people believed before, that, I mean, there's an angle and the angle goes away and then material becomes chiral. But turns out that this angle is still finite according to them at 350. So that means that the domain itself remains chiral. So this thing is still chiral, even at that temperature, and presumably that will go away at that second phase transition. So putting this information together, I mean, that's all I can do at this point. It's yet work in progress, but I would think that this is where chirality sets in the domain, and then the angle occurs between them, right? And so this is all kind of beautiful computational work they do in order to derive to these conclusions. I was actually very impressed by this analysis. Now, coming back to Liang's talk, kind of it's now obvious to me that, well, we need to look on the symmetries of these modes. I don't know, but if they have particular symmetry, let's say they are E-symmetry modes, then we can say which one is which one is left-handed and which one is right-handed. You have them on different energies in that case, if I understand right. So I need to understand why there are different energies also. So there are a few puzzles we need to talk. Okay. All right. Yeah, so they also look on the temperature dependency, and they say that at high temperatures, so this is the initial picture, and on cooling, the size of this domain grow, this blue region, interdomain region, gets weaker and weaker, and then presumably they don't have that data, but they believe that at the next phase transition, everything becomes pink or something like that.
Any questions?
So, yeah, so your data show that above this was thought to be the CW temperature, there's already some chirality sensing. I wonder, just some random thought maybe, could this be due to some kind of vestigial order?
Yeah, that's a good, yeah. So that was, well, when my student brought me this data first time, I said, well, maybe the sample is straight. Maybe there's some strain. Yeah, exactly. That would be the signature of the same thing. So we tried many clips, we tried many samples, and so far it's a delicate thing to make sure that there is no tail because of induced broken symmetry. Right. So I'm not ready to publish that. It's the same question I asked, but that's only part of the puzzle. The other part, of course, is that the modes have different frequencies and all those things, and this comes together. And I had exactly the same explanation as you brought up till I saw this STM data, which also says that there is more than one transition. If I believe, well, they have only 3 temperatures.
So I have 2 questions, actually. I don't see the plot of this intensity as a function of temperature. I mean, do we have that? I mean, instead of this color plot, just a line plot. I'm just.
Well, I don't have that line plot in this.
Yeah.
In this.
Yeah, I'm just wondering if that intensity is sort of a tail-like, maybe just a large critical range of chiral fluctuations. They have been seen in magnetic systems.
Well, I mean, it's too high for the fluctuations, I believe.
No, I mean, if you have the chiral fluctuations in your domains developing, I mean, what you see is the chirality in the phonon mode, right? So it might, I mean, it's a possibility. In magnetic system, it has been seen that dynamical chirality develops before the static one.
Sure, right. But then you would expect it to be strong at low frequencies than at high frequencies. You wouldn't expect new mode appear at etc. There's some. Yeah, so that's another explanation.
Yeah.
One is the fluctuations. Well, 20 degrees a little bit high.
Yeah, but that's.
Yeah, no, I understand that dynamics can be, yeah, I understand that.
And then
Okay,
critical
so then, I mean, induced broken symmetry was even more reasonable to me, but we tried on many plates, we tried many times, it always happens at the same place. It's kind of consistent data.
The other question is just practical. What is the size of these chiral domains in the ordered phase? I mean, are they like resolvable in micro-Raman mapping or something?
Oh, no. They are set in lattice constants.
No, those are small things.
Right.
But in the temperature range, when you say they become, spanning the entire sample.
Right, but okay, so the picture here is that.
Because your talk is next. I don't want to make you tired.
Yeah, the picture is that, so those are atom size, those atomic really size domains, and that's the region's interdomain. So this is the interdomain region, and then those grow, but they are still very, very tiny.
Okay, not Raman.
Yeah, no.
Thank you.